Two narrow parallel slits separated by 0.85 millimeters are illuminated by 600 nanometer light, and the viewing screen is 2.80 meters away from the slits. What is the phase difference between the two interfering waves on the screen at point 2.50 millimeter from the two narrow parallel slits separated by 0.85 millimeters are illuminated by 600 nanometer light, and the viewing screen is 2.80 meters away from the slits. What is the phase difference between the two interfering waves on the screen at the point 2.50 millimeters from the central bright fringe? Second, what is the ratio of intensity at this point to the intensity at the center of a bright fringe? Well, let's start by pulling out the information in this problem and organizing it in a data chart. So as I already pointed the notations on the picture, D is the separation between two slits. So D equals 0.85 millimeters. Let's remember for the future that this is not in meters. We might need to do converting, and are illuminated by 600 nanometers light. That means it's the wavelength. Lambda is a 600 nanometers light, and the viewing screen is 2.80 meters away from the slit, so R is 2.80 meters. Now, what is the phase difference? So which means we're looking for phi question mark for the case part A, and for part B it says what is the ratio of intensity at this point to the intensity at the center of the bright fringe. The intensity at the center of the bright fringe is the maximum intensity, so they want us to find intensity at the point divided by intensity at the central bright fringe is a question mark. Now, for part A, let's remember, what do we know about the phase difference? We know that phase difference equals K D sine theta, where the K was the wave number and it equals 2 pi over lambda D sine theta. If you forgot this, I suggest you to view one of my videos called Intensity of Interference, and I derived this equation in that video. Now, if we look at this equation, it seems like we have the D, we have the lambda, but we don't have the sine theta. How can we find the sine theta? Let's go back to our picture again. And the interference would go, what is the theta? So this is the point we're interested. This is the theta right here, okay? And if we highlight this triangle right here, you can see that's a right triangle with one side to be y, another side to be in r. So the hypotenuse would be square root of r squared plus y squared. So from here I can find the sine theta. Can write here sine theta equals y over square root of r squared plus y squared. Now let's plug this one into our expression for the phase difference and rewrite it again. So we will have phi equals 2 pi over lambda d y over r squared plus y squared. Well, what we can do, we can plug in the numbers and move on. But you know, in physics, before blindly plugging in the numbers, we would like to actually simplify things a little bit. If we take a quick look at this expression, r squared plus y squared, y is in a range of millimeters, right? So r is in the range of meters. If you add a millimeter plus, it is a 0.85 millimeters. When you square it, it becomes really, this term becomes really close to zero. So we can neglect it. Can be neglected. And it's interesting that I just noticed that I forgot to put the square root in here. Okay, here we go. I corrected myself. Now, when we neglect this term, then the square root of r squared becomes an r. So apparently, phi can be written approximately equals 2 pi over lambda dy over r. Now we have a way easier expression where we can plug in our numbers. 2 pi over 600 times 10 to the negative 9 meters times 2.8 meters. On the top we have the d as a 0.85 times 10 to the negative 3 meters, and for y we had a value that I forgot to put in my list. So y equals 2.50 millimeters. So this is what I'm going to plug it in here. So 2.50 times 10 to the negative 3 meters. Punching this into our calculator, we will get 7.95 radians. So this would be the answer for the first part of the problem. Now for the second part of the problem, which is related to intensities, let's see what we know about intensity at any point on the viewing screen. We know that intensity at any point in a pattern equals I naught cosine squared phi over 2. So this expression I found again, or rather you can hear about it, and I derived it in the video previously made on intensity of interference pattern. So from here I can say the ratio of I over I naught equals cosine squared phi over 2. All we need to do, plug in the value of the phi. So cosine squared, now our value was 7.95 radians, 7.95 radians divided by 2, and that will give us the result of 0.453. Thanks for watching. Stay tuned for more to come.